repulsive? Attractive, right? So think about when attractive interaction, your pi t, internal pressure, is positive, okay, for attractive interaction. And what that means is when A is positive, this is positive, right? Okay, so what's going to happen is when I have an expander volume, when I change my volume to be plus, that's an expansion, right? When you do the expansion, your internal energy change is positive. Your internal energy is going up, right? So it's like these two molecules used to have an attractive interaction, and by increasing the volume, bring the molecule apart. So it looks like there are a lot of attraction in this one. It takes energy to separate those away. So your internal energy going up. Okay? Or in other way, if A is negative, there's a repulsive interaction. And what that means is because of the repulsive interaction, the energy is already high, and if you bring them apart, your internal energy will go down. The sign is the opposite on this. There's many ways to understand this. The one that I like is actually the other way. Delta V is negative. You know what's that? That's a compression. If we bring the compression, if there's attractive interaction, if you bring the molecule closer and closer together, the internal energy is coming down. Okay? Your U is going to be negative. I'm talking about when A is positive, attractive interaction, and your internal energy is coming down because they like each other, they bring it closer and closer, so there's more attraction into this. Okay? So you guys can see this meaning on that. Okay. You guys can handle this, right? Yeah, you just start with this, okay? And to see how am I going to deal with, and you guys remember when I talked about their state functions, so obviously I wanted to do the same thing with H. Later we're going to do the other things. The next portion is going to be the same thing here. And my choice is this, whereas this one choices will be pressure. Because of the pressure is my pick two choices in addition to temperature. And you guys can do the same practice. Yes. Okay. Okay, so you start to see some, I guess, a first introduction of something that is describing the real gas properties, and then this is an internal pressure that can be essentially measurable. You can measure U can be measured on heat under constant volume, volume change keeping the temperature, and you can measure that, and there can be a description of how you can quantitatively describe this property of the real gas. Okay, so number 3. So I'm going to throw this one. Change in the internal energy now, and then in this case, I wanna do change in the temperature, but this time I wanna keep the pressure constant. How about this? Oh, this is different because the internal energy change, when I change my temperature, keeping the volume constant, that's the constant volume heat capacity. But this is on the constant pressure, which is sort of typical, right? So there is an interest for people to understand. This is a very generic interest. Okay, under constant pressure, when you change the temperature, how fast is going to be the change in the internal energy. And that's the one that I need to work it out. And this is also another nice practice of an exact differential. So I'm gonna write this. du is my peak two choices, volume change, temperature change. Guys remember? And then I'm going to say that's an internal pressure, that will be CDT. So that's the same equation that I wrote it before. And then what I'm going to do is I'm going to do the operation saying, okay, I am going to divide this by dt. dt. So everything is in dt here. And by doing so, and I guess this is done, and this equation is simplified. And what I'm going to do is, because I cannot really, the meaning of changing the temperature is not like a single dependent variable. So meaning is I'm going to impose a constraint, P, constant pressure. So now I'm going to put an additional constraint here, and then this one becomes pi T, volume change, temperature change, constant pressure. So this equation becomes like this. Something that probably we want to know, under constant pressure, when you change the temperature, what is the internal energy change? Now, this is something that I can measure. This is something that I can measure. And then you have to deal with some new variable, which is this, which is a volume change. You change the temperature and the constant pressure. So how am I going to deal with this? So this is a new quantity of interest for me to deal with. Okay, so starting from here, I got to know, and then I just have to figure out how I'm going to describe, and this one is coming down to this way. And let's take a look at that equation. So what do you see on the top? Volume change. Right? What do you see on the bottom? Pressure change. So when you change the temperature, the volume is going to change. Makes sense, right? If you guys remember doing some kind of a balloons or something, you put in a hot water bath, things expand, right? And when you change the temperature, volume is changing, and this is what we call thermal expansion, right? Must be related to this quantity. All right, and then we are going to say the meaning called thermal expansion constant, or FEC. We call it alpha, and then let's define the alpha. That was actually introduced in the first class of this. I just wanted to show the input versus output. So let's kind of take a moment, like a pause, and then restart something that what we can do as a person who is related to this. So this is what I'm going to put it in here, but let's just start to have a fresh new start. And this is 1. There's a bunch of numbers. This is 2. Think about thermal expansion. So let's think about what's my input. My input is temperature change. Increase my temperature, and I observe your response, output. I like the response. Your system responds in a way, volume change. But I have a little bit of the problem with the volume change, because volume change is an extensive property. So this volume, if you have a 1 liter, the volume increase delta V versus if you have a 10 liter, the delta V is not the same. But what I'm conceptually interested in is relative volume change for a given volume that you have, right? So what you need to do is the one that is actually meaningful is 1 over volume times the volume change. So that's the quantity that you are interested in. And this is something that the real volume change, that is an intrinsic property of response of the system. So therefore, the thermal expansion constant is, I want to know my volume change in a way normalized when you change your temperature and keeping your ambient pressure the same. So that's my definition of thermal expansion constant alpha. And then I'm in business here, because if you look at here, what can I write? Can you write here? Yep. Volume times alpha. And then you're going to go backward, right? You right there? So what? All of a sudden the quantity, I want to know internal energy when I change my temperature, but I want to know the real system, right? Or real case scenario. The constant volume is pi d internal pressure times alpha times volume plus CV. So this is one equation that it came out. Okay? And that's a good practice for you. I think this is the whole point of this, when you to have an exposure on this kind of mathematical notation to kind of express your ideas, right? I want to know if I change something, this is a response system, like more meaningful responses, normalized response, and let's define some new variable, and you want to call, what's the natural way of calling it? Thermal expansion constant. So that's how you do it. And then now we got to measure that and tabulate it, and also now we have a final form, how internal energy, when you change the temperature, this is all measurable. And then there's the volume. It's just a practice for you to. Okay. There. This is. I think that they're going to cut me anyway, so I'm going to continue. I think that this camera just decided to cut me in the middle and generate new video, so I think that it's okay for me to finish up another one, which is called the compressibility. So I just bring out the response when you change the volume, the response is the volume. So the number 3 is what is called the isothermal compressibility. Okay. I think that this one also makes sense, and we want to learn how to put this word into an equation. This is what this purpose of it, right? So I want to know how easy to compress this gas. All right. So what are you putting as an input? What are you changing? You apply. I want to say compressibility. So are you applying temperature? No. What do? You're applying pressure. And your responses? Volume. But like I said, the volume is depending on your volume itself, right? So if you see that, okay, so I think that I'm going to write this way first. I'm changing my pressure, right? And I want to measure the volume change in a normalized way. That's what this is about, right? That's a compressibility idea. And then what? And you say, I have to further define, because volume not only depends on the pressure, but also temperature, and I want to make it clear that this is an isothermal compressibility. practice, right? Right. So this is a good practice. And then this one is we call kappa heat. Okay. So that's the isothermal compressibility. Okay. So now I'm not done yet. Okay. So think about it. Look at here. Before and after. So before, after. I apply compression. I apply pressure. So I guess my delta P is positive. You know, when your pressure goes up, right? What is the response from the system? Your volume change is going to be going down. Your volume is going down. And this is what you see, right? I apply pressure, your volume is decreasing. So what I'm saying is, the sign of this is not matching, right? When you apply pressure, final pressure is higher than your initial pressure, your volume is going to decrease, so your final volume is smaller. So this is inherently this is a negative term, right? And if you want to say like this is the same idea. Do you want the tables of negative numbers, or do you want to redefine? Just simply put a minus sign in front in the beginning, so you only deal with the positive numbers. And then obviously the choice is, I want to make an equation containing negative number, so this whole thing is positive numbers. That's the definition. Okay? So isothermal compressibility has a negative sign because of the mismatching the sign as the system responds. Going back to here, right? If you increase the temperature, your volume is expanding. So I don't have a problem of the sign here. But the other one, I have a problem with the sign.